So, be handy if I could find my little pen. All right, so we're going to look at only how to find average velocity, instantaneous velocity, and then we're going to use the tangent line to approximate slope. We'll do the rest of these tomorrow. And you might be thinking, well, how does a tangent line have anything to do with average or instantaneous velocity? And it has a lot to do with it. So since we're starting calculus, I would highlight this if I were you. So highlight that. Calculus is the study of change along a curve. So what that means is, I gave you a little graph here, so I'm going to plot a nice little parabola. So a little sad, but there it is. And then I'm going to plot some points along this parabola. Just choosing some points at random. And then that top point we're going to assume is the vertex. And so if calculus is the study of change along a curve, the important aspect here is that slope shows this change. What item do you usually associate slope with? A line, right? You've never been asked to find the slope of a curve, ever. And so we're going to actually use tangent lines to find the slope of this curve, but the slope of this curve changes depending upon where you're at on the curve. The slope at this point is different than the slope here, is different than here. It's different at every point along this curve. So it's kind of similar to velocity. If I drive from my house to school, do I drive the same velocity the entire way here? No, I start at 0 velocity. I speed up, I slow down, I speed up, I slow down. Do I ever have a 0 velocity? If I'm stopped at a stop sign, stop light, you know, whatever it is. So there are even periods of 0 velocity. So same thing on a curve. Your velocity changes. It increases, it decreases. It can even be a 0 velocity. It can even be undefined on certain curves. And so we're going to use what are called tangent lines. Do you remember a line that's tangent to the circle from geometry? What is a tangent line?
It touches one point of the circle.
Yes, it touches one point on the curve. It does not touch 2 points on the curve. If it touches 2 points, it's a secant line. So a tangent line might look like this. And bear with me, I'm not using a ruler, but oh, I missed it. That was terrible. Oopsies. Let's try again. There. So let's assume that it actually went through that line, but it's touching that curve in one place. So there's one tangent line to the curve. From this point right here, I can draw another tangent line. Would you agree that the green line is different than the red line? They're different slopes, aren't they? You should be drawing this too. And then I'm going to draw another tangent line. This one at the vertex, the line at the vertex is always going to be horizontal or vertical. It'd be vertical if your parabola opened right or left. And we're just using a parabola here. We're not using a curve that's to the 3rd degree or the 4th degree or the 5th degree. So we're making it simple by having something to the 2nd degree. And then I'm going to choose different color. There's another tangent line. Now my tangent lines are becoming positive. And then finally, oh, let's go with light blue. So the point is I can have an infinite number of tangent lines around this curve. There's an infinite number of points on this curve. So there are an infinite number of rates of change. And isn't velocity also a rate of change? In our car, isn't velocity miles per hour? So that we could actually show certain velocities as a curve. And so we're going to look at some problems further along. We're going to still try to keep that parabola up there. But the first term that we're going to look at is average velocity. So highlight that. Average velocity is just like I was saying. If I start from my house and come to school, I speed up, I slow down, I go around curves, through valleys, hopefully not through buildings, although you know I am Mr. Magoo and can't see, and then I arrive back at school, right? And in all that time, I'm speeding up, slowing down, stopping, all that kind of stuff. but couldn't I find an average velocity? For the distance I traveled and the time that I traveled, I can find an average speed. And some of you have cars that have computers in them that actually can calculate the average speed that you went for a particular trip that you took. My car, not so much, but some of you have a little fancier cars than I do. We're going to calculate it here. And so average velocity is quite specifically the change in position divided by the change in time. So your change in position means distance. Just a fancy way of saying distance. They like to oh shucks, what did I just touch? I hope it was nothing. The change in distance is denoted by S, not D, because D in physics tends to be used for, I don't know, density or things of that nature. They use D for other things. And in math, we start to use, in higher level math, D starts to denote a derivative, and so they like to stay away from D. So we're going to use S, like it or not, whether it looks like a 5 or not. And then time, we're going to use a cursive T. So if I'm going to find average velocity, velocity sub-average, so AVG, is equal to the change in position, which is delta S, divided by change in time. Your starting position, or I guess most likely your ending position minus your starting position, divided by your ending time minus your starting time. In this particular problem, example 1, you're told that an automobile travels 120 miles. Isn't this our S, right? In 2 hours and 30 minutes. And this is our T. Well, they have not given you a beginning distance and an ending distance. They've given you the whole distance, haven't they? So you don't have to find delta S. They gave it to you. Delta S is the 120 miles. But if I had said, I want to know the average velocity from mile marker 5 to mile marker 150, wouldn't you subtract those two? And so then your delta S would be 145 miles, right? So there could be some problems, so you have that. This is an easier problem. And same thing with time. I could have asked not, for the whole 2 hours and 30 minutes. I could have asked for the average velocity over the first hour, from the end of the first hour that I drove to the end of the 2.5 hour that I drove. So the difference between those two times would be what? 1 hour and 2.5 hours. What's the difference? An hour and a half. So that would be your delta T. But in this case, that's not what they're asking. So for here, our velocity sub-ab is equal to, just for your note purposes, we're going to write delta S over delta T. And then our S is 120 miles. And our time, we cannot put 2 hours and 30 minutes in there for the time. You either need to have it in hours or minutes. What do you think the preferred would be?
2.5.
Hours, yeah. Now, 0.5 was easy because 30 minutes is what portion of an hour? Half, and that's a decimal equivalency of 0.5. And so what if it were 15 minutes? That's 1/4 of an hour, which is what decimal? 0.25. Well, what if you had 53 minutes? What would you do? 53 over 60. So no matter what you do, you can take your minutes and put it over 60, and then just you're going to have a calculator, take your calculator and divide that out. So 30 over 60 is 0.5. So we have 2.5 hours. So take your handy dandy calculator and divide that out, please. What do you get? 48 mph for miles per hour. So that was a freshman physics problem, correct?
Yes.
Easy. You only have one or two like this. All right, so we bring that in. We talk about average velocity because we need to know the concept of average velocity in order to find what's called instantaneous velocity. So for our next problem, we're going to look at instantaneous velocity. That means the velocity that I'm going, the speed that I'm going at a specific point in time. and that's what your speedometer on your car shows you, doesn't it? At any point in time, and that'll go up and down. Think of go back to here and think of this line changing on the parabola at any point in time. Remember, that line is representing the change that is occurring. And so our velocity, that instantaneous velocity, is that change that's occurring that's going up and down. But it's interesting to find out, why can't we use the average velocity formula for that? Instantaneous velocity involves division by 0. Why would that be? Think of it this way. Our change in, well, let's just look at change in time. If I want to know how fast I'm going 1 hour into my trip, at that 1 hour mark, boom, isn't that just a snapshot of time? The difference in my time would be 1 hour minus 1 hour. Wouldn't that be 0? Because I don't want to know a whole second. I want to know that one instant in time. It's just a snapshot. And so, is division by 0 possible? No. And so, therefore, division by 0 is necessary, but not possible. And not possible. So it's considered undefined. Well, by this time you should have realized that we can always get around things that are not possible and figure out a way to do it. So somebody you should be well aware of, Newton. What's Newton most famous for? Dropping the apple, which is the law. Yeah, it's law of gravity, right? But he actually is most textbooks will tell you that Newton discovered calculus. However, there is another mathematician at the same time, not in the same place. They're not best buds. They're not working together. And that person was Leibniz. Weird name, not Galileo. We'll come to Galileo in a minute. But they both discovered calculus at the same time. And this necessity for studying the change along a curve, or the area under a curve, is also another thing that we're going to be looking at. But Newton invented these things called fluxions, and Leibniz invented differentials, which will lead to differential equations after Calc 3. You haven't even taken Calc 1 yet. It's lots of fun stuff to come. And these both explained instantaneous rates of change without resorting to zero denominators, which was nice because now we had a possibility of finding instantaneous velocity at that one point in time. Both involved mysterious quantities that could be infinitesimally, I can hardly say that word, small, without really being zero. In other words, we're going to approach that time. So I said 1 hour. If I want to approach what my speed is at 1 hour, I'm going to approach all my speeds at 1 hour and 1 minute, 1 hour and 30 seconds, 1 hour and 20 seconds, 1 hour and 10 seconds, 1 hour and 1 second. What am I doing with my time each time? I'm getting closer and closer and closer to 1 hour. I'm approaching 1 hour with my time. What have we called that? We've done some of this year. It's called what? Well, yes, convergence is a way to put it. Correct. What? Nope. Although it could involve an asymptote. As I approach a particular number, remember we call that a limit? Right? What is the limit? In other words, what's the y value of the function as we approach the x value? That's what we're going to do. So as we get closer and closer and closer to that point in time that we're looking for, you're going to see that the y value, which is our velocity, if you will, is going to approach and get closer and closer to a particular number. So let's look at example 2. We are going to be using limits to avoid zero division. Galileo, another famous mathematician that you should be familiar with. Leibniz, not so much, but Galileo and Newton, definitely, right? Well, Galileo apparently had nothing better to do than to observe balls going down an incline. And he discovered a very interesting thing. When rolling balls down ramps, he discovered that the distance traveled was proportional to the square of the elapsed time. The distance traveled was directly proportional, should also be in there, to the square of the elapsed time. So remember, distance is s, time is t, and so he discovered this relationship. Distance is equal to t squared. Distance is equal to time squared. So if I know that my time that the ball rolled down the incline was 5 seconds, I can square that. My distance will be 25 units of some sort. It's not negative. That was, okay, it's not negative. The negative is just separating it. Yeah, it's a hyphen. So you can look at it that way. So we're going to look at the problem. A ball rolls down a ramp so that its distance s from the top of the ramp after t seconds is exactly t squared feet. This t squared feet we got from Galileo. We know this because Galileo discovered it. So that's where that function comes from. What is the instantaneous velocity after 3 seconds? This 3 seconds, they're telling you, is the time that we're trying to approach, which is 3 seconds. So we can use limits to do this, but in order to explain why the limits work, we're going to do it by hand, and we're going to find values using our calculator and get ourselves closer and closer and closer to 3 seconds, and we're going to try to figure out what our instantaneous velocity is. In other words, what is it approaching? So how do we find instantaneous velocity by hand? So let's go ahead and go find half. You have a blank page on the back of this. Only use half of that blank page, because you're going to want the other half of the blank page for later. So on the very back, yeah, the very back. So I'm going to put a new blank sheet up here. And if average velocity is equal to the change in s over the change in t, consider the following interval. My writing looks like a kindergartner's. Consider the following interval. We want the interval to go from 3 seconds to t seconds. In other words, this is interval notation. I'm going from 3 seconds to some seconds greater than 3, and including those. So way back in last semester. I want to take my calculator, which we'll do here in a minute, and I'm going to create a table of values. And I'm going to have some values I choose for that t that I'm going to put in my table. But we have to come up with the equation that we're going to use. And we have to find our instantaneous velocity at a particular point. And so we're going to do a couple of problems by hand. So here's the first problem. So that was actually a 1 in there. So our first problem, if I'm to find change in s over change in t. Okay? Remember, how do we find distance? What did Galileo say distance was? Time squared. So which one of these is the bigger time? The t should be the bigger time because it's on the right. So if that's my bigger time, what is the distance at t seconds? What's the distance?
Greater than 13.
Nope. What did Galileo say distance was? No. T squared. So isn't that the distance at t seconds is t squared? Distance is s. This is the part that's going to be hard for you to swallow at first. So my distance is t squared for t, because we're doing change in distance. So the numerator is distance. Well, distance s can be swapped with t squared, right? They're equal. Okay, so that's for when we don't know the actual time. Then we're going to subtract from that because we want to find the difference between my distances. This one we do know is 3. What's the distance at time 3? 9. How'd you get that? Because you squared it. So we're going to take in here and we're going to square it because it's t squared, and just for your note purposes we're going to put in the 3. And then that's divided by. Now in the denominator we're going to find the difference in our time. Well, our time are 3 and t. Which one's bigger? T. So to find the difference between those two, wouldn't you take the bigger and subtract the smaller? That's what we're going to do. So we're going to take the bigger, t, and subtract the smaller, which is 3. That's our general formula, and let me just show you why it works. So think about it this way. What if we chose a value for t, and let's just say our value was 3.5. That means that t over here is 3.5 and 3. So we're going from 3 to 3.5. Let's find our difference. So equals, whoops, I need my equals. So my t is going to be represented right here by 3.5. So that's my bigger out of the two, 3.5 versus 3. So I'm going to put 3.5 in here, and I'm going to square it. And I'm going to subtract the smaller time, which is 3. And I'm just choosing 3.5 because it's close to 3 seconds. You can choose whatever you want. And then we're going to divide that by 3.5 minus 3. And let's see what we get. So if we take our handy-dandy calculator over here, and we'd use parentheses, 3.5 squared minus 3 squared, which you could put 9, divided by parentheses 3.5 minus 3. What do we get? 6.5. Well, that's a 6. Shocking but true. So that's our first problem. Then problem number 2. Let's do it again. What do you want to choose this time for t? Get close. No, get closer to 3. You want to get close because you want to approach 3. So if you chose 4, you'd be going away from 3. So what'd you say? 3.25. Okay. So we'll choose 3.25. You all agree that's closer. So to find change in position over change in time, wouldn't we take the bigger between 3.25 and 3, because our t now is 3.25. The 3.25 is bigger, so it comes first. Waiting for what? No. Number will never get negative because we'll keep approaching 3 but never go past it. What number do you mean is negative?
Like the 6.5 and then we're waiting for that number.
No, watch what happens. So then we've got minus the 3. Oh, shuckers. Cancel. Oh, goody. That's what happens when you try to not to write on there. All right, and then our 3.25, this is our time, minus the 3. So we have our change in position, which is our distance, which is t squared is distance, t squared, over your change in time, which is t minus t. So run that through your calculator, tell me what you get. You get 6 point something, I'll guarantee it. Run it through your calculator. What is it? 6.25. Wasn't that closer than the 6.5? All right, so you can do this again and again, but my point is the only thing that's changing each time is this first one and this first one down here keep getting swapped out, don't they? The 3 squared and the 3 down below stay the same. So this is my general formula right here. Right here, this is my general formula, and we're going to put that in our calculator. So go to your calculator, and we're going to go to y equals, and we're going to clear out what might be in there. And I'm going to clear my key press history. So we're going to put in parentheses, because if you don't, you'll get it wrong. And we don't have t, so we're using x. So parentheses x squared minus 3 squared, and you can put 9 in there. That's fine too. Parentheses divided by, and you must use parentheses, x again instead of the t, minus the 3. Because we're approaching 3, that's why the 3 never changes. And so if you look at the graph is actually interesting. We don't really care about the graph for our purposes on here, and let me show you the larger screen. It looks like a line. And we'll come back to this in a minute. I'll explain why it looks like a line and not a curve. But what I really want you to do is go to table. So go to second, table, and I want you to put in the table here the numbers that we just put in. So put in 3.5 and hit enter. Did we get the 6.5? Yep. Then put in the 3.25 and hit enter. We got the 6.25, right? So let's put in a closer one than 6.25. What about, or 3.25? What about 3.1? Put in 3.1, hit enter. Is that, what's that number getting closer to? 6. Put in 3.0001. Isn't that super close to 3? Hit enter. What do you get? So what number is this approaching? As x approaches 3, what number is this approaching? 6. That's the instantaneous velocity at x equals 3 or at t equals 3. And so we're going to go back to our question example 2. So let's go back to that first page. Okay. So we want to treat this as a limit. And so we don't have to do all that by hand. That's why we're going to discover, well, how do we use a limit to get the same answer? So write yourself a note, treat as a limit. So what we just did was the y. Why are we going to do what we're going to do now? So treat as a limit on the interval (3t). Remember why I chose 3t? Because our time is 3, that's what we're approaching, and then we always want to go to the right of 3. You could go to the left, but who wants to? It's harder to go to the left. Write yourself a note that this t, based upon what we just looked at, represents the time getting closer to 3 seconds. So that's what that t represents, is that time that we keep choosing that gets closer and closer and closer to the 3 seconds. And so we'll write it as a limit as t approaches 3, because that's the time that we want to approach. And then we came up earlier in our work with the general equation. And the general equation is always the original, and so remember, this was our original, right here, this was our original function, so it's always the original function comes first. So your original function, t squared, minus, then we're going to take that original function t squared, but we're going to plug in what we're approaching into it, that 3. So again, before we do the denominator, the original function t squared, this is still the original function, but what's plugged into it instead of t? The 3. The 3, which is what we're approaching. And we get the t from here, because that's the bigger, and the 3 comes from here. Then over, it's always the variable we're using, t, minus what we're approaching, 3. So that's what we're finding the limit of. Do you notice that this is the difference of 2 perfect squares here? T squared minus 9, isn't that the difference of 2 squares? Isn't it factorable? And so we get, don't forget to put your limit in here, I do it constantly, the limit as t approaches 3 of t plus 3 times t minus 3, all divided by t minus 3. 99% of the time, this denominator should cancel with something in the numerator. I say 99% of the time because I will always give you one at this level, this stage that you're at that would, because otherwise it would be crazy for it not to. And so, as you can see, these do cancel, and you're left with a simplified, I like to call it a simplified limit, the limit as t approaches 3 of just t plus 3. So we're not done, because we haven't found our limit of 6, right? So then you're going to take this number that we're approaching, and you will always plug it into however many t's in this case there are in that simplified limit. So we're going to replace the limit as t approaches 3 of 3 plus 3, which coincidentally equals what? Isn't that what we found using our calculator? So you could do it with your calculator, doing it the long way, you know, plugging things in and looking to see what it approaches, but using limits is so much quicker. Less work. Are there questions about that? I know that that was a whole lot more difficult, Jessie, than the average velocity. She's vastly taken with all this. I know. I'm just hassling you. So is there any questions about what we did and why? Does that make sense? Okay, and so at that specific point in time, and so let's go back to the graph here. So hit graph. So I'll use the bigger one. At 1, 2, here's time 3. Go all the way up to the graph at time 3. What's the x value? 6. Isn't that fascinating? So the instantaneous velocity at that point, and this is just the graph of our function. It's not the graph of t squared, but, you know. All right, so then let's go on to the page after this. So we're going to look at example 3. So now we're going to find the slope of a tangent line, and it says use limits. Use limits to find the slope of the tangent line to the graph of, and here's that Galileo's equation again, s equals t squared, at the point, and we have to fix something. I wasn't thinking when I made this point up. We need to change this. Oh, I don't want that one. We need to change the ordered pair to, oh, I did change it on here. Yours is not fixed. So you need to change your paper so that the point reads 2, 4, and also that the limit is as t approaches 2 here. So please make those 2 changes. The only thing that's important is if they give you an ordered pair is the x value. This is the x value, in our case, the t value. So isn't this right here t? And what's the 4 represent? Isn't that s? The y value is s. And so if we square our time of 2, don't we get a distance of what? 4. So that point actually works in the equation, which the other one that you had wouldn't have worked. All right, so I got you started here. I'm going to find our limit as t approaches 2. Why 2? Because our time is 2. So our t is equal to 2. The 4 you don't need at all. 4 is not going to help you in this problem. And I'll show you another way the problem's written when we're finished with this one. And so we have to find our change in position. So remember, what do you think the interval is going to be for this one?
T2. No, 2t.
The interval would be what to what?
2 to t.
2 to t. Very good. Does everybody understand that? We're approaching 2, and so that's the start of our interval, and we want to go to some time to the right. So again, you could choose, 2.5 and find your distance and position divided by your distance and time, and then you could go to 2.25 and so forth, but why not use limits? And so again, what's your original equation or your original function that they gave you? So so this is the limit as t approaches 2 of our original function is the t squared. That's your original function, t squared. So it comes first. And then minus always the original function, which is t squared, but you're going to plug in the value you're approaching. And aren't we approaching the value of 2? So it goes second. And then in the denominator, you take your variable t, and your variable t, no idea what that did, and you subtract what you're approaching, which is 2. And in this particular problem, don't we again have the difference of 2 squares in the numerator, right here? So this can factor, and I'm going to go ahead and do it down here, equals the limit as t approaches 2 of t plus 2, t minus 2, So minus all divided by t minus 2. So what's happening? Yep, these cancel, which is what we want. And so, sorry about that. And so we have the limit as t approaches, and this becomes our simplified limit, if you will, of t plus 2. What do we do with that? You're going to take what we're approaching, the 2, and you're going to put it in for every t that you have. Well, we only have one t. So this equals, because I'm running out of room, the limit as t approaches 2 of 2 plus t, or plus 2, equals what? 4. So the instantaneous velocity would be 4 at time 2. It's also the slope of the line that's tangent to the graph at 2. So if you went here and put into y equals, just clear that out and put in x squared. And look at the graph. And here is x equals 2, right here. Could you put a line right here? And would that have a slope of positive 4? Or could it possibly be? We obviously are not checking it for sure, but it's a positively sloped line, isn't it? And that's what that's telling you. All right, the last thing we're going to do is you're going to turn it back over to the very back of your notes and use the other half of the blank part. And we're going to do one last problem. This is going to be example 3A. And please write all of the directions so that it means something. And so we're going to find the slope of the tangent line. Sorry. To the graph f of x is equal to 2x minus x squared at x equals 2. So we've gotten away from velocity. We've gotten away from Galileo's s equals t squared. And we're going to use that same theory of average velocity, instantaneous velocity, and the fact that change is represented by slope of the tangent line to any function that's a curve. And wouldn't you agree that 2x minus x squared would be a curve? Isn't it still a parabolic curve? Okay, so we're going to use limits. So this equals the limit as x this time, because we're not using t, approaches what value? What value are we approaching? 2. Notice that you're given x equals 2. You're not given an ordered pair this time. I don't know what the y value is. I don't need to know the y value. And so that's what we're going to approach because they want to know what's the slope at x equals 2. Well, this time it's not going to be, x squared minus x, or x squared minus 2 squared over x minus 2. It's not going to be that because that's not our function. Our function is not x squared. What's our function? The 2x minus x squared. So you start with your original function, 2x minus x squared. So that's our original function, minus the original function again, but we're going to input, wherever there's an x, the number that we're approaching. So the number we're approaching is 2. So as you can see here, this is our original function. We didn't change it. Minus, there's the original function again, 2x minus x squared, but instead of x, we put a 2 in because that's what we're approaching. What's going to go in the denominator? Our variable x. That part doesn't change. Our variable x minus what? 2. So then you're going to do some simplifying. What's 2 times 2? 4 minus 2 squared is 4. So doesn't that make 0. So you're going to write more steps than you normally would because these are your notes. So the limit as x approaches 2 of 2x minus x squared minus, and we actually get a 0. We normally wouldn't write this step, but I want you to be able to see in your notes where some of this stuff came from. Does everybody understand where the 0 came from? 0 came from this part right here, became 0. So really what we have is the limit as x approaches 2 of 2x minus x squared over x minus 2. Now remember, I told you that that denominator should cancel into here. In order for it to cancel, what do we have to do here? Factor. And most of you are going to say take out an x, which is fine. Let's see what happens. The limit as x approaches 2 of x times 2 minus x. Go away. Go away. Erase. Over x minus 2. What's the problem? These cannot simplify. Instead of taking out an x, we can rectify this by taking out a negative x, because that'll change this sign to negative 2, which is what we want, and this sign to a positive x, which is what we want. So instead, we're going to factor out x as it approaches 2. We're going to factor out a negative x. And that will give me x minus 2 up top and x minus 2 on the bottom. And then we can cancel out the x minus 2's, and our simplified limit as x approaches 2 is actually equal to negative x. What do we do with that? Put this 2 in for just the x, not the negative x, just the x. And so most of you are probably running out of room, so this is equal to the limit as x approaches 2 of negative 2. So what does that equal? It equals negative 2. Well, let's see what that looks like. So let's go back to your calculator, go into the y equals, clear that out, and you're going to put in our original function 2x minus x squared. That's our original function. Look at the graph. And at 2, isn't this, well, let's go over here on the big screen. Isn't this where x is equal to 2? If I were to put a tangent line, wouldn't it go in this direction? Isn't that a negative tangent line? Is it conceivable that it could be negative 2 for the slope of that line? Yes. So are there any questions regarding that and how it all correlates up to the average velocity and instantaneous velocity? It all rolls up together in one. Isn't that fabulous? I love it.